have with us Professor Marija Ilic from CMU, Carnegie University. I know her since she was a student, and she is one of the world's leading authorities in smart grid and all related problems. She graduated in 1980 from St. Louis, where Professor Marija comes from also. And she has been associated with several institutions as a professor, including MIT, Cornell, and she's an honorary professor at Delft. And she has been now for about 12 years with CMU, where she directs the Center for Smart Grids. She's involved in many activities in smart grid standards and modeling and so on and so forth. And her most recent book is on engineering IT-enabled sustainable electricity services, the tale of two low-cost green Azores Islands. And she was telling us that she's just starting a new program with NIST on modeling and smart grids. So we will have plenty of time to interact with her over the next few years, given our program. So with that, we welcome you. Today she's going to talk about smart grids, end-to-end cyber physical electric energy systems.
Thank you very much, Baras. Good morning, everybody. Thank you for coming. I have a pretty long talk because everybody says, what are the smart grids? And it's hard to wrap up your hands around it. And one of the hardest things is how broad you go and how deep you go. So I'm going to struggle with that. So if I start doing something that's obvious to everybody, just say, keep going. Or, well, depending on how much time I have, like 1 hour, right? I will try to cover most of the things that I would like to share with you, but I may not get there. So the first thing is it's important to work in power systems, and I'm going to leave some slides. I'm not going to go over them, but I just want for the record to make sure that it really is not an industry to neglect, and it's been neglected for a long time. So what is more interesting is when we were for dinner last night, the professor said, well, what is to change? Everything works. So it's sort of hard to identify what are the things that you can make better. And so here are some things that, after a lot of thinking, we think need much more improvements that everybody talks about, maybe not as good reliability as we would have, more frequent interruptions. But there is a more interesting thing, which is hidden inefficiency in today's system. When the lights are on, how efficiently you are utilizing what you have. And that's getting to be much more of a problem than in the past. So there are studies that have very well documented studies for typical utility in power system in system interconnection that you can save up to 25% of fuel costs, economic efficiency, if you manage outages in an online way rather than reserves, for example. It's a huge, huge potential saving there. So these are these hidden things that come from using smarts that are hard to explain. So the other thing is, as you know, there is more and more for environmental reasons, there is more often effort to deploy intermittent resources. And if you don't do it in a smart way, you have to put one-for-one, something that balances the system in a fast way. Storage is something expensive, and that doesn't pay off at all, right? So economics are not there. So you have to do it in a smart way so that you deploy renewables and at the same time the cost doesn't go to do it, and so forth. So there are things that one could improve, but making the link between what needs to be improved and what we know about the system and how the system is operated today, it's really big step, and that's what I would like to share with you, some of the things that we've been working on. Another thing that we've seen since during this administration is there has been actually quite a bit of investment into rethinking power systems doing smart grids. But if you think about it, there are improvements in hardware, power electronics, better switches, more efficient switches. I talked with Alireza, for example, on Friday, how to include power electronics into smart cars and so forth. For the system, for large-scale system problem, that is a node in the system. So we are thinking more about how all these different hardware interacts in a smarter way. And there have been a lot of small-scale demonstrations so that people familiarize themselves with the resources. But so there are new physical architectures that are evolving, but cyber architectures are sort of trailing behind. And that's one of the big issues that we are working on. One thing that is clear in cyber, but it's not very formalized, is that what used to be top-down, utility-based work, with objective in which utility decides everything to keep the grid uninterrupted and so forth, it's moving more towards customer-centric, distributed level. What are the objectives to meet at the user-centric level? And that raises all sorts of questions for different disciplines, cooperation between users, aggregation, and so forth. So the field is changing, but maybe this is a biased opinion on my side. We are still very short in formalizing, how to rethink the problem. So I first want to share with you this thing that I've been very excited about. So the question is, how do you rethink the problem, and what may be some unifying way of thinking about the problem, so that you now understand what are the smarts doing to the system. So several years ago, I discovered the work of Eleanor Ostrom, who basically has done some pioneering work in water systems, in which she basically looked at water systems as resources, users, and governance system. And depending on the characteristics of these core variables, she calls them, these characteristics of core variables, temporal, spatial characteristics, contextual, who is doing what, they determine how sustainable the water system is going to be. So if you have very proactive users, for example, who maintain water resources and so forth, the system is more sustainable. So it ends up at the analysis level. What we have done is we end up doing, and I think it's one possible unifying thing, how one could think about the role of cyber physical systems in the social ecological system. So it's not just the engineering system, social ecological system. You have resources, users, and it's within certain social environments. So is it possible to link sustainability with CPS design? That's really the question that they began to help me put things together, and I want to share it with you. So there are these core variables, which are resources, users, and governance systems. They are their characteristics. They change fast with time, if they're proactive users, whatever. But then there are these deeper level variables. If they don't interact, if they don't work together well, then you have to understand them. And where Eleanor stopped in water systems, she really didn't do the mathematical modeling. It was a concept. You look at all these characteristics and you can say how sustainable. You can compare systems for their sustainability. We wanted to take these for energy systems, we call them SES, social ecological energy systems, as the basis for establishing maybe one possible unifying principle for designing CPS and for energy systems. So what we are talking about here is, it's very simple actually. This is her Nobel Prize winning article in Science. This is the picture. You have resources, you have resource units, governance system, and users, and the interaction and the outcomes. That's all. This can be water system, can be energy system, can be water and energy system together, multiple heterogeneous systems. And I did this like a couple of years ago on the continuing supply briefly. You can begin now to think about smart grid as physical grid, electric power grid, and its cyber to make the given social ecological system sustainable. Begins to do something for us which we actually don't do in power systems. We design electrical machines, we design power electronics, but we design pieces and we don't know what the whole system is going to serve. So please keep this in mind that we are going to think now about, this is our working definition, about smart grid as physical. I have these resources and users, I have to somehow interconnect them. Do I need a grid? Don't need a grid? How much wires you need? And that depends on how smart I make those wires. And also, so there is a trade-off between how smart, how strong, and how smart. Chinese like to talk about this. And then how they both serve sustainable objectives of the system.
How do you measure sustainability?
So can I go a little bit to the top and then I will return to that top? Because it depends on what architecture you have. Okay, sometimes the governance system defines it in a top-down, sometimes it evolves, and I'll return to this a little bit. So what are we talking about now in power systems? What does it all have to do with power systems? So for people who haven't seen power systems, these Gs, these are conventional generators. These Gs in green may be some new resources, clusters of photovoltaics, clusters of electric vehicles, wind, etc. You can have also responsive demand. And they're interconnected somehow. So this is the way the system is going to evolve in the future, the simple model. It's a circuit interconnecting these devices. And so the question is, how do I make this system sustainable, and what does it mean? So the story gets very complicated very fast. So if you want to capture everything, there is a very real danger of complexity. Model everything in detail, what they're going to do with it. And so the technical problems are very fancy and lend themselves to fundamentally different specifications for online data, models, and cyber design. That's one big thing. So now how to do that, actually, I'll go through some of this work in progress. And the other thing that's really interesting about evolving power systems, now for the first time we have real data, it's incremental data, so it's no longer possible to separate measurement, communications, control specs. Really, they all have to, there is a trade-off between very advanced distributed controller or some communications. And I don't have time to do all the examples, but basically, there are trade-offs all over, in between high-tech part and the smart grid, and also between its effects on the grid and the complexity of the cyber. But I think a lot of people are working on the question of what can be, because of simplifications, what can be done in a distributed way and what must have fast communications. And power systems people hate fast communications because they don't trust it to maintain. So here are some arguments for, so what Eleanor did, she basically had this vision. It's very coarse, doesn't have the modeling. So one of the big questions is, how do you actually go to the level of detail to model the multi-physics that you have, multi-temporal, multi-spatial, multi-contextual dynamical systems, so that you actually do the design for performance, and also it's very nominal dynamics. So there are all sorts of complicated things underlying this complex grid, but one thing is for sure that information and energy processing are intertwined. And so, going back to the picture again, what we've seen in the fundamental concepts of modeling is very coarse. Actually, it doesn't even exist. There are some tables that say you should watch for those properties of the variables. Now, what does that mean for my future power system? You've seen pictures like this. We have conventional resources. We have all sorts of resources interacting. And the thing to make it even more complicated is what people refer to as restructuring, is that different entities may be different owners and they make different decisions. So these decisions somehow by different owners. So you're not designing the system as one. There are different decision making interacting over time and making the system evolve or perform in a real time better or worse. So how do you go to the classroom and teach these things? First of all, you have a heterogeneous system. We have energy conversions of different things. We have to do the control design for guaranteed performance and so forth. You really want to bring the system. This is our take. We want to think about the problem as nominal dynamical system in which there are some states, initial conditions, and the system evolves, and it's being shaped by different control designs. States can be heterogeneous. Depends on how detailed I model the energy conversion in electrical grid. So the complexity of the interconnected electric grid is determined by many things, determined by complex interplay of component dynamics, electrical interconnections, and by highly varying exogenous inputs. This is what we didn't have in the past, the intermittent resources and so forth. So you end up having this tough problem where you have multi-physics, multi-temporal, multi-spatial, multi-contextual, and you want to make the system sustainable. So this is what we've been doing, but this is sort of in hindsight. This is not how we started. We've been doing different pieces of this intelligence, and then a sort of framework evolved. What's clear is that it's not one method, so it has to be a framework. So given social ecological energy system, given resources, given the very large system in which I have nuclear plants and far away transmission lines and aggregate loads, passive loads, right? I need to build one type of wires, and I need to build one type of intelligence to align the interactions between them. If nuclear plants has flat output, users better have a lot of adaptive demands so that supply and demand balances and things like that. So this really helps me, as you'll see as I go to different architectures, how I put the specs for what I'm designing. In order to make the case for that, I think what we've seen is at least 5, that goes to the question of what's sustainable, at least 5 different types of future electric energy and current grids. Both power systems the way it is now, fully regulated, can be the same one, just restructured. And then you have this mix of very large plants, small plants getting on the system, and they're all trying to work together. And then there are microgrids, where I have fully distributed electric systems, and development sustainability is very interesting because it is a different objective for developed country, different objective for developing country. So the main challenge, this is, when it's all said and done, what we are struggling with, what information should be collected, processed, exchanged to minimally coordinate this multi-level system. That's what we've been doing. And one thing that is helping us, that this must be done with careful accounting of the underlying social ecological energy system. It's not the same intelligence, it's not the same physical, nor cyber. And it all boils down, I want to talk a lot about these interactions as the technical part. And one thing that the sort of label of our electric energy system group at CMU is these DYMONDS, dynamical monitoring and decision systems. I'm going to show you how today's cyber for today both power system is evolving in this dynamical monitoring and decision system. And it's basically natural evolution, but it's going to take time to get there. So this is again for people who haven't seen these wiggles, are large conventional power plants. Blue wiggles are smaller intermittent resources getting closer to loads. Loads are denoted by these arrows. So these are utilities. They have their own objectives. So other utilities, they're interconnected. They may have the HVDC power to control flows, or they can have free flowing. So this is your bulk power system. A lot of them don't have direct switching to control how much gets exchanged in the area. So this is your architecture one. Okay, now I want to talk about interactions. Interactions are very, very peculiar. They are interactions across the multi-physics, the intertemporal, the interspatial, and the contextual. And depending on which architecture I'm working on, they're going to, one is going to dominate the other one. So this is just 101 power systems, very quickly. Okay. So if I have this bulk power system, I can think of the generator connected by wire to the infinite bus. This is an ideal voltage source. The rest of the system is so robust. It can absorb anything. It behaves like ideal source with complex voltage, constant voltage magnitude and 60 Hz frequency. That's the reference. So just the simplest translation I tell my students, we are teaching smart grids this semester. This is how I can think if I want to connect my wind power plant to very large bulk power system. This is how I model the rest of the system. It really is something that is going to stabilize me. There's not going to be interactions problem. Okay? I'll just connect and I'll be fine. So the simplest physics is electromechanical. I think about rotors moving, and this is the dynamics of rotors, speed of the generator and position. And if I model, I want to show you some very peculiar things. If I model this system as electromechanical model, I don't worry about magnetics of the generator. I'll get So here is where the control comes in. If I don't have additional damping control, governor is a damping control, then the system, all the variables oscillate all the time. Because the energy exchange goes on back and forth between the generator and the infinite bus. If I have good damping, that's the governor, and every generator has a governor control that responds to the deviation of speed from synchronous speed. Sooner or later, I stabilize. So notice here, let's say, if I have infinite bus, these time scales are important. For this tuning of the governor, I set to in 10 seconds, for example. These are just representative numbers. Now, this is something, as I'm teaching the course, I just discovered for the first time. If I'm thinking now about connecting the generator to microgrid, well, this is not going to be infinite bus anymore. It's going to, and I have to be very careful how I model the rest of the world. So I model it, these are just exercises from the class. I model the rest of the world as constant, absorbing constant real and reactive power. Everything else, without governor control, with governor control, now it's taking much longer to settle. Okay. It's really interesting because that means that on microgrid I have to be a little bit more careful about sensitivities. So case one is, oh, this is another thing, just very quickly because it's important in power electronics. When I specify power absorbed, I have two solutions, right? Because for voltage and angle for equilibrium. And one solution for this case one is one solution, another one, in this case, another solution. Completely different dynamics. I can have one stable or unstable. This is just electromechanical. So this is this interaction across the physical phenomena that I want to illustrate. And if I think about my load as constant impedance, then it's going to be dragging here quite a bit. We don't know these phenomena. These are just new questions because we didn't worry about it. When you tune wind power plant from GE, you basically tune it against the equivalent to your dam for stability. Now, depends on what you are connected to, there may be some problems. So this is the relevance of representing the rest of the system. It's also helping me thinking about these three different architectures electrically being different.
And the Mellon and Baras have been computed for this
Yes, they do that for the worst case, for the waves outage. That's how they tune the controllers now. Now, on the same thing, I want to just emphasize goes back to Professor Abed's PhD thesis. If I don't think about my generator just having electromechanical part, but also having magnetic part, voltage dynamics, voltage behind the transient reactance in general, for the generator, if you are into that modeling, we are going to get actually now the nonlinear model because the electromechanical and the magnetics are interacting. And now I have a controller which is going to control the voltage at the terminal to stay there. That's one controller, field excitation of the rotor winding. And then I'm going to have governor control that's going to control the valve position to put more and less mechanical power to apply to the rotor winding. So these are two basic controllers, but they're very different. Governor is damping, AVR is controlling voltage, magnitude controlling how much power is sent to the rest of the world. We have to understand the physical roles of these controllers rather than just doing it, because they have very different things. So one of the questions, book just came out of Sandia, very good book, I forget the name of the authors. It's along these lines, what is the damper control can do, what is the, and using Hamiltonian Darwin and so forth. But I'm not talking about this example for those reasons. I'm talking about this to say that what we don't understand is what level of detail you need to represent in your physical system in order to design cyber right. So I shared it with my students this semester. So if I just represent the electromechanical, I model everything looks stable. So it can be oscillating, I put a damper, it's fine. Now I got into nonlinear dynamics. I have this is cumulative change of a phase angle difference between infinite bus and my generator. Frequency, if you zoom in a little bit more detail, frequency is not quite at 60 hertz. We have the voltage oscillations all the time without control. So this is really maybe, when it goes to model verification, am I verifying this model or am I verifying the other model? You have to be very careful about what physics I will be verifying. With governor control, I can stabilize it. And that's another thing here. Can stabilize it. I still need some coordination to bring the system frequency to 60 hertz. I can be a little bit off. But we'll talk about that some more. With ADR, I get good control. But frequency oscillation happens, I need both. How do I prove it? But I have to understand. So what we have shown in this other architecture, this is hybrid, this is the second architecture, third architecture that we have there. If I have small resources now and I aggregate them as portfolio with their own sub-objectives, that's what that the sustainability objective will be now, that this is portfolio with their standards and they are loosely connected to the rest of the system. Or I even have what Fred Schweppe used to talk about, homeostatic control. Everybody regulates itself perfectly, and the system, like the body, regulates itself. Then, if I think about these islands that we simulated two, one very small, had hydro, geothermal, diesel, and the idea was to replace diesel by wind. That was the whole idea about in the book exercise. So what intelligence you need to put there so that there is no operating problems. And San Miguel is a little is larger island. But let's see the simplest thing. If we again use just in the classroom, on this small island, have hydro, diesel, wind. I can model wind as negative load. What comes just gets dumped and scheduled in, and then the other generation is controllable if we need to demand. Or I can also control wind. I can get two different approaches. Now, this is my microgrid, right? I'm talking about Flores. I do the same experiment. This is with as real data as we can for Flores. This is not even hypothetical data anymore. You have different responses, and then this is just a little snapshot from the book where you compress all the loads now as constant impedances, get rid of them, you just have these three power plants, hydro, wind, and diesel, and then you have the dynamics of the mechanical part, you can have dynamics of the electromagnetic part, the same way as on the simple example I showed you. Now something really strange happens. If I just do model, I tune my governor to stabilize frequencies, and then I look at the coupled model. System goes up. Okay, so the question is, what's real? What is mathematical fiction? I think for the first time in power systems, we actually have opportunity to ask these questions, because with Jose Mura, for example, we roll these things. You can postulate the model and do the parameter identification. You can do different things. So we've done the simulations for these islands, and the next thing would be to actually go and do the experiments to double check data, and so we are getting there. But this is the first time to say, okay, this is this cross-coupling interaction across physics. So what people do in their optimizations in today's power systems, they say, I assume the ramp rate of the power plant. Well, there's a lot of energy conversion there. Nuclear plant looks different than hydro and so forth. We just replace that by constant ramping rate. When is that it's important to have more detail, when it's not important? And one thing that is sort of also clear from the studies that we've done so far is that the system operator cannot be done. All the details of a very heterogeneous system cannot be done by the system operator. So how much do you internalize? That's $1 million question. Because I can represent very, very detailed dynamics of my wind power plant, and then give some very simple function or go, no-go intent for the system operator to do.
In this model, the coupling was there in the model?
Yes. So here is, I tuned my governor as though it's not there.
But you designed the control without taking into account.
Right. And people do that all the time.
I understand.
So it's a big surprise, right? But you have to do it in order to raise the awareness, even to educate ourselves. We were not sure. Okay. So it goes back now, so you can have interaction variables which are spatial, temporal, and I want to talk more about, because that has been sort of history in power systems, the temporal and spatial, because we have many, many components. So this is our working definition. It's a formal definition. I'm not going, I can give the references and so forth, but several students are working on this. These are variables associated with subsystems that don't change when you disconnect them from the rest of the system. And it can be shown that they exist. You can just look at the mathematics of subsystem as function, its own local dynamics, couplings, and its own local control. And one thing, this is a fancy way of saying that each subsystem matrix actually is rank efficient. What that means, if I disconnect the system, there's going to be power imbalance, because I don't know what's the time. So it's that rank efficiency that's actually telling me that that interaction variable exists. We started doing that even with my happens long ago for EDF or multi-voltage control, but this is the linear version. So there exists such a transformation at the subsystem level, which in the linear case is the linear combination of its own internal states. You don't have to know anything about the rest of the world, so that the interaction variables only depend on the disturbances from the outside world. And so this is the basic thing that's beginning to tell us mathematically what is interaction. And so this is an important thing because in hierarchical control, in today's power systems, we assume that the fast phenomena is localized and the slow is, the scheduling is local. So that is not necessarily true. If I have strongly coupled subsystems, and again, going back to the beginning of the mathematics, just the same equations using the, so if I have strongly coupled system, now they interact. If I have weakly coupled system, completely different dynamics. So how does that help me? How does that help me with the specs, with the design? Okay, so I just did the background, what's happening. So what we've been pursuing, and it's sort of, I think it's almost there, but it's still also work in progress. So what you want to do at the subsystem level, at the zoom-in level, you want to do your internal control, but at the zoom-out level, you want to somehow coordinate interactions. And it buys a lot, because in weakly interconnected systems, you have, those are slow, right? You don't have fast communication. You don't need fast communications. It also is reduced information exchange. And so Xi Jinping just finished his PhD thesis. I think they're going to try activities in China. It's scaring me, but they want to do so. They want to do minimal coordination of subsystems so that your performance objective, this goes down to sustainability. At that time scale, I want interactions to be such that the cost of interactions is minimized and the cost of control. The quality of interaction is minimized. I can control inter-area oscillations and all that just by building it as a control problem. But it's much lower order control problem than the one when I put all the states, when I get one flat. And again, don't have too much time to go into that, but power engineers have been very ingenious. For them, these dynamic interaction variables in steady state, let me just give you the result. That's basically area control error. This is total imbalance at equilibrium. But when you have a persistent wind perturbation, you cannot think about equilibrium. So you need the generalization of interactions in the dynamic sense.
So this cannot, can this be computed?
Yes. Yeah, yes.
But in a systematic way, not theoretical.
In a systematic way, but this is what the stimulation.
So if I go to the LNG representation of everything,
yes,
are these invariants actually?
They are unique up to constant.
They're invariant.
Yes, they're invariant basically. So all of these, you start from dynamic model, I didn't go through all, but you find this transformation, and it's actually the book with the worst. So we started, we've been playing with this without actually understanding what we've been doing for a while. And then what is important now in the context of smarts is, I think this buys you a lot, right? If you just if you do coordination in terms of interaction variables. I'm not going to get there, but one.
But if I have, what exactly is meant by dynamic interaction variables? Am I referring to the time scales? Or?
So interaction variable is, let's say I start from time 0 to time t. It's the energy exchange, right? So the rate of change of interaction variable, rate of change of energy is basically power that comes into total net power. So it has a physical explanation, linear and nonlinear.
This is what's meant by dynamic interaction.
Yes, yes. You can write, I don't have to write it just for an equilibrium.
Okay.
And I'm just talking about linear version, but Milos Cvetkovic is doing the nonlinear version, and it actually leads to a lot of nice nonlinear controllers for guaranteed performance. So, why is this so important? This is important now that I go to, for example, some very real life examples, and I have, we need to avoid emerging problems, right? So you put a lot of PVs in Germany. You go to West Berlin, then there are PVs on all roofs, right? Well, it turned out that people, the system operator, are beginning to see the frequency deviations. How are you going to control this one? So, just going back, because I may not have time to go back to emphasize this later, I just don't want to lose it. So, this coordination, this is where Shishi and Liu spend a lot of time. You can either do it to have the coordinating entity in terms of these minimal interaction variables, and the million-dollar question is, can I do, is there at least sufficient condition that lets me do it in a distributed way? To come, and so what it boils down to, we have sufficient conditions like from Schiller's book on minimizing the interactions. So basically, this thing is going to be stabilizable, for example, if the strength of interactions is weaker than some rate of change at which dynamics in the subsystem changes. That's the translation in words. So if I have that, then everything's fine. Everybody can stabilize in a distributed way. I don't need a coordination. Then the only question becomes the question of optimality. How much am I helping each other? And where you may still need some coordination. But here, in a distributed way, if that condition is not satisfied, then you can do, in a distributed way, cancellation of interaction variables. So basically, every subsystem is responsible for itself, and they look like decoupled. So there is a price to pay there, but it depends on what the rules of the road are. So you can do it both ways, and we are just finishing that paper, but what is fascinating, if I have these architectures where I have systems with very small inertia, like wind power plants, strongly coupled, each one unstable, they together are stable. I don't have to do any coordination. If I have the same system, very weakly coupled wind power plants, and weakly coupled, they need some power electronics and stabilization because they cannot help each other and so forth. So you can, through this mechanism, you can actually, through this sufficient condition, you can, at least it's conservative, but you can check the sufficient condition. When do you need additional coordination? When do you need to cancel interactions, and where you just do your stuff and you're done?
The coupling here is through the
electrical
or the other part of the system?
Electrical. So, yes. So basically, this controller, philosophisation, for example, governor, we are going to cancel, it's going to send more or less power, cancel the power flow exchanges, basically synchronizing port and things like that. Yeah. All right. So,
In this coupling, you calculate both real and reactive power, or just equal?
yes. So it takes all sorts of students, you guys, sorry about it. So one thesis was just electromechanical part, linear, Shishin. Then Milos does everything, coupled, nonlinear, interactive, because you need that for power electronics, for fax control.
If the topic is not the reactive power, that's very important.
Right, and like I showed that example, things look stable, but they actually may not be stable at all. So, and that's very critical with power electronics. And, or you need the dynamics to, for example, when you want to control the reactance of the line to deliver more or less power to the slower, mechanical devices, then you're always sort of controlling how much reactive energy is stored in those wires. So without that model, you cannot do anything. Okay, so just to close this part is basically, it's going back to hierarchical but not quite. So we call these SBAs, smart balancing authorities. So there are all sorts of open questions. If these are given boundaries, you can just check the conditions. More interesting question is, I completely agree, how do I build boundaries in an aggregated way? So I don't need that much communication. It's all open, okay. Now I want to just very quickly go through, so.
Can I ask, what do you communicate?
You communicate basically in this interaction variable, if it's coordinated, that's net cumulative. If I have these subsystems, it's net accumulated energy by different subsystems. And that has its model that's driven by controllers.
Once you communicate with it, not with the system.
You can, so two things. One, you can give it to the control center to communicate, to coordinate all the interaction variables. The other one, you just cancel the net power flow, basically, which is the rate of change of energy. And again, I don't have time to talk about nominal version. It's almost done.
If you go to the first model, is there any delay?
And that's all open questions.
Do you have to study the delay?
No, that's an open question. That's the thesis, and that actually comes up all the time. That's in the thesis, yes. So there are pros and cons. So what's interesting about smart grids, and I know that you work a lot on trade-offs, there is no free lunch. You either get more communications or delays or smarter control. Something needs to be fixed, and so it depends on which technology we are talking about. So what do all these things mean now for different architectures? What's the state of art in both power systems? And everybody is talking now about online big data, right? Okay, so can you improve anything in the existing systems? All sorts of things. You can do more, better. It boils down, if you go through this, it boils down to optimizing the schedules of reactive control devices, more so than industrial in a nutshell without going to mathematics. And there has been some work also done that if you monitor these interaction variables and control them the right way, you can online actually prevent the blackouts, and that's more involved versions. So there are things that you can do.
If you're fast.
Yes. Well, so if you are fast enough, that was the comment. If you look through the list of contingencies that utilities now have, I would say 90% of them are not time critical. 99% of them are not critical. So you need to understand a little bit the dynamics of what's time critical, what's not. And yeah, and one thing that's real catch-22 is that what's time critical may not become time critical once I embed smart automation. And that is where the automation phase. So there is also, we have to just tackle it from different things, but different sides. So all sorts of things, all sorts of issues in today's operation, the assumptions made and so forth, I'm not going there. So I want to talk about how we're going to, what is possibly the next step in both power systems, in the first architecture. So the sort of general thing is that going from single top-down coordinating management to multi-directional, multi-layered interactive IT exchange. That's what, and I will put some pictures. So that's what we call DYMONDS. So in order to answer this question, we need new models, new decision tools for self-commitment and clearing such commitments, etc. So different time scale, different things. And different students have been working on that. So now this goes to communications. What do people know in real time now? They measure, this is the large control center at the bulk level, they measure down to the sub-transmission level, distribution level, which is, let's say, 69 kV. And that information gets processed here. They never know what's happening in the distribution networks. That's the bottom line. That's how it's being done now. There's a lot of now effort with smart grids to put more smart scale communications. But that's still very disconnected. So if you think about this in terms of graphs and information graphs, basically there's a lot of information going from 69 kV there, nothing inside there, and nothing back, right? That's the bottom line. Yang Wang is working with Rohit Nagy on PhD on that. So now, why this may not work? Because all these smarts, they are closer to the distribution level. So what we are advocating and we've been working, is sort of evolving into formalized framework to have physics-based modeling and local nominal stabilizing control, new controllers for storage, for demand, for etc., new sensors to improve observability. And you have, if you embed controllers into these new devices, you have much more controllability and observability for the first time. And then use the interaction-based, variable-based modeling approach to manage complexity. So that's the basic idea. And it goes over different time scales. So what does that mean? That means I have to figure out, this is one PhD thesis, the guy is working on clusters of electric vehicles. How smart charging you have to have, what information needs to be exchanged with the others, on which time scale. It all comes together nicely. And this is our sort of stateful picture. You put diamonds of different kinds, and diamonds offer information exchange. It's very simple. Going from stopping here, not having embedded intelligence in system users, having it all. Now, what is the problem with going forward in both power systems? The problem is, we learned it very hard way, that state estimators just basically don't work. In a nutshell, the state estimator today is that system operator collects redundant data from about the loads and generators down to 59 kV. So it's snapshot. For the next hour is going to be that much. I do least square estimation. That's it. But that's snapshot. Static least square estimation. Get what is the state, voltage, and angle. Forget about it. Restart again. And that is the basically law of the land in power industry. So there are problems. First of all, it's nonlinear when you add reactive power, and historical data are not really used at all. And there is this daunting question of how to include PMUs. Where do you put them to actually improve the state estimator? Okay. So these are some things that Yang Wang is working on. I put the details because it has a lot of methods here. You know, each box is different method for. So you can go from nonlinear static state estimator to SDP type estimator, like people are doing in Caltech for AC optimal power flow, just by convexifying it using semi-definite programming. It is shown you can get better results. Where there is much more low-hanging fruit is how to use historic data to actually learn the system by non-dependence, right? And power system dynamics, yes, periodicity, there is daily, there is weekly, there is very fast time scale. So here there is a lot that one can use. And then this one, the last one, is very intriguing because, let me go there. So you can ask the question where to put the PMUs. Put them there. So you do the optimization to maximize the so-called information gain index. And you actually got the answer for 14-bus system that those are the best locations to put the PMUs. This is maybe the first type of work going on because people are talking about putting PMUs to make the graph statically observable, reachable. And this is very different. This is, you would increase the information gain. You would get the information index gain.
So information index gain means the best possible information on the state?
Yes.
That's what it is.
Best possible information on the state under uncertainties. And Rohit Nagy and Yang are working on this. So you can put some bounds within which you can do it.
That's the criteria.
The criteria is to maximize, minimizing the distance between what you think you are and he had LP, so it can be more than one. P can be anything, it can be L2 or L1, or I think he played with several. Okay. But this is a very different way of asking how do you use PMU because they need to complement some accuracy at the 2-second level, but they measure, once a cycle 30 measurements. How do you average those 30 measurements that are noisy into one cycle? So there's a lot of stuff to be done, and I have to say this is very biased statement, but cannot do any optimization. I do a lot of optimization for online scheduling and so forth. Cannot do anything unless you go to the state estimator. End of the story. So the state estimator.
But all PDS are not create a record.
Yes.
So if you identify it as a people.
Yeah, so that's some of the work that Rohit is working on with Yang. Like if I have, we'll start with this model to see what are the most critical locations to put in this.
Because you try to average, that probably is not a good.
No, it's not a good idea, right? So it's more in terms of some, depending on which node you take, LP or L1 or L2.
Are the PMUs very expensive now?
No, the installation is expensive. This should be
So
the
why don't they put them in everywhere?
They should, and I think there is a trend. In China, they are, yeah, right. But the thing is that one thing that's different from when I was a grad student, now the system could be very observable and very controllable, all distributed things. So the problem is different, right? Okay, so I just mentioned about it. But an interesting connection again is how do I use this online measurement to manage my interactions? I am not interested in everything and if you put the two together because not every measurement, as you say, is serving the same purpose for me. So there is all sorts of stuff that PMUs can be doing, and this is again in the context of demand variations in real time and what you do. Scheduling depends on what time scale you are in, but this is where we are maybe going. So you have these perturbations, you put PMUs, dynamic line rating. This is your online automated regulation for things that I cannot predict. Scheduling is different from predictable component. So there are all sorts of open questions here that I'm not going to go through. We have done some earlier work with using PMUs as more accurate and faster sensors for automatic voltage control. This was stuff that we did with atoms long ago, but now it can be implemented easier. And depending on where you put the controller, depending on where you put the sensor, you're going to get very different outcomes. You're going to stay within the reliability limit or not. Okay? So that's what this slide was showing.
Do you have enough data now to produce?
For this one is no-brainer.
To use learning to the model?
So the learning, I think this is why these DYMONDS and distributed object-oriented stuff is interesting because at the distributed level you can do it. At the system level you cannot do it. I just don't see how you can do it at the system level. But an interesting thing is this is pushing the envelope. Can you actually have these very fast deviations, solar or wind, being held by something else in another area? If I have hydro here, can you even talk across the sub-areas at the fast time scale? Because regulation is no longer steady-state concept. The wind power is almost stochastic continuous. So you can do it, and again, you have to be very careful about what's interacting in a strong or weak way, not to have some very fast subsynchronous interactions and so forth. So it boils down to, can I have standards for correct performance? It's huge space for rethinking things, and I don't think that I have time to do that one, so I just want to go to one.
How confident you are that all these linearizations, linear models that I've seen, that are used widely, are actually valid?
So that is only with new measurements now we can say something. We don't know answers yet, that's the next step. So we've just done simulations. So I just want to show you in 5 minutes completely different thing here that we are very proud of. This was at the beginning, right? Just 3 more minutes. Thank you, Reza. Yeah, so this is the simulator for scheduling. It's not even for regulation, right? I predict the wind, I have the model predictive models for maximum power, and can I replace basically these conventional dirty plans with this was little sheets with PhD thesis when he's at Texas now. So can I put 20%, 50%, and not get problems? Very interesting thing come out, and this is more of a issue of really the smarts affecting and having data affecting what you can do. So if you just treat wind as a negative load, right, this is going to be a negative load. Yes. So if you just do static dispatch, as I said, you have one snapshot, you follow basically this wind goes up, you predict it's going to go up, the very fast plant has to go up. So you have to get this 1-for-1. This is what's very expensive. Now if I do model predictive control, I smooth out things, I predict. And I didn't have time to go to the math of that, but it's very well documented in the papers we published. So basically, it doesn't pay off to use all the wind. You either spill it or store it. And that's very hard policy question, but it has savings on gas. I don't have to build a very fast responding plant for it. What's more interesting is that it is, depending on what your look at horizon is, you're actually going to, in the slow power plants, you're going to utilize them better in the more predictive way. Because you're going to look longer, you can start them up, don't just turn them on and off. So there is a huge saving in using all the resources. Now the difference between the dotted line and the red line, which is centralized versus distributed, is that's what it is. So there is a little bit of quality gap. And the question is, with more learning, can you do better and so forth. So the rest of the diamond goes okay. So this is what I have to do to, this is what my power plants would have to do to manage predictive wind. And I have to spill a lot of wind, unless I start doing adaptive demand, right? So now I do the adaptive demand. JY is finishing, she's also going in academia. So his demand becomes adaptive, and now as this net load, which was inelastic, is going to come down as the wind doesn't blow. So I don't have to have a spike in gas. You can smooth it out. So demand has to be symmetric, managed in symmetric way. There are all sorts of questions. Does one trust that the demand will do and so forth? So it's a question of protocols and the language and communicating, but it's doable. And then electric vehicles the same, they are demand. So you can either end up with this very high charging, spike for when you have a lot of electric vehicles, or you can spread them around in a more predictive way and do well.
There'll be some papers where they describe this adaptive pricing using this predictive.
Yes.
Does a lot of people do the same? So is that somehow?
This is an excellent question. Yes. So so the thing is that I talked to Madavish, for example, about it. If you do it without model predictive way, you're going to get instabilities. But model predictive is always yes, you're going to capture. So you have to do it smart way. It's not unique answer, but I think the whole point is that you have to be very careful. What are you after? And so, just to finish, it's really huge huge opportunity, but very likely won't be explored, given the industry and whatever. And I didn't have time to talk about privacy, but I just want to make one comment that the more you internalize at the distributed level, the more private you can be. And so there is work going on that. This is the one that I'm spending a lot of time on, and we have time to talk about. Value, in particular, of cyber is system dependent, right? I don't put responsible for everything, or I don't put 20% to solve environmental things. I have to be very careful. So capacity-based thinking in planning and system design doesn't apply here very well. So we need to work more on value flexibility, just in time, just in place and context. And they all have their value. This is where we are now, and actually stuck. Because we finished these demonstrations or simulations showing that it's possible to have these CPS paradigms, proof of concept. Now, what is needed to develop user-friendly simulators to educate what this means so that we don't just talk to ourselves. And to educate people who are decision makers and people who want to adapt this, and then link that protocol to giving incentive. So it is tough, very tough, because even if you do these simulations, then all that sort of questions you were asking about, what does that mean? You have to do the physical verification, all that, but at least there is some system here of thinking about how I can, you give me this system or the other, and I need to do different things, and I can formalize that mathematically and as a dynamic problem, and that's what I wanted to share with you. Thank you.
Have a question?
Okay, I didn't talk so much.
Okay, I have a lot of questions.
Yeah, something.
Yes.
You were talking, that was very interesting about estimating the state, doing the best estimation possible of the state. Sometimes you don't care so much about estimating the total state vector, you care about part of the state vector. Has somebody formulated that, or some aspect of the state dynamics?
No, because for the first time we are beginning to even understand. I'm trying to say that these interaction variables may be something that's important to estimate. So it depends on what you want to do. No, that's the next step. I don't know anymore. I very likely have lost everybody, so. Any questions from the students, no?
So there's this problem that everybody tries to solve is distributed, and we're discussing it. There's a lot of new interest about the power flow over a network.
Yes.
Any comments on that? How you fit this framework where you actually try to do over different scales and time and space?
So I think there are several things, right? One thing is Andrew is working on this. Can I actually, so what he did, so the power flow can be formulated, solving the equilibrium can be formulated as solving set algebraic equations, or it can be also formulated, he did it as like Azores Islands did as an optimization of flows in the complex network. So if you go that way, you can actually now do it in distributed way.
How fast?
So that,
Because the
Oh.
Azores Islands is very slow.
yes. So that is the problem, but the thing is that, I mean, this is a major breakthrough that you actually can have lines and generators talking to each other and deciding what the equilibrium is going to be, rather than just relying on the system operator. So there were two patents, and I think one company already acquired both. Yes.
Do we guide this implementing?
Yes. And that's a wire company that wants to put smarts into wires to talk to each other. And that's for situational awareness for many things that they're thinking about. But it is very slow. And so there are often questions on how do you speed up. But that's the equilibrium question. New question is, if I don't think about my node of the wires, really good, an equilibrium can I extend dynamics with faster time scales. And there, flow will be even more of an issue. So. But with Azores algorithm, what was a contribution there is that those algorithms of flow maximization, of distributed flow maximization algorithms, they are only for transportation networks. They don't observe cubic flow as long. So the contribution was how are you going to get around that problem.
But I would add the triple bloods as it was saying.
Yes, and that asks for more information exchange.
But
So how are you going to make it distributed? That's where the contribution was, that was the pattern.
But you can use Mendel-Lagrange, correct? Anyway, that's another story.
With Andrew?
No, you gave us an idea of Wilson, right?
Yes.
Yeah. The real question I have is, what are you going to do about security? That was the paper we did with Leon, that he talked to you before he left. Lab network optimization part with quality constraints. Remember that?
Yes.
You don't know.
We don't know.
You gave him the idea to do a Mendel-Lagrange. Anyway. Remember that? Anyway, what are you going to do about security? Because
So-
we now have two examples where there have been targeted attacks where with very simple calculations you can introduce 40 vectors, particular of these sensors, and blacken a particular area. This will happen in Brazil twice because they wanted to make a couple of factories out of functionality for a couple of days. So what's going on? And the problem is this: the more you go to smart grids and the more distributed generation and production, the more this is a problem.
Well, I think you can look two ways. So one is I can be distributed remain smart, and even without encrypting, I can exchange the information that you cannot reverse engineer for what you need. So Sanya, the workers we saw at the conference, basically if you have two utilities, let's say at that level, and they, right now, they don't trade and they don't coordinate because they don't want to exchange the data about cost of generators and so forth. But what she came up with said, okay, this utility doesn't have to know everything about every single injection. It only needs to know what is the effect of that scheduling in the other area, on my own area that's known as loop flow, right? So nobody can, it's very hard to reverse engineer from loop flow back to what the individual is doing. So I think it's a very ripe space for more work, but I think it's not going to be done unless you understand again what are you trying to hide and what can be hidden. And it's again about these effects. You have to know the effect, but you don't have to say everything, right?
What about structured type attacks, where there is this famous picture of the Department of Homeland Security where they saw this wind power turbine. It's completely destroyed because somebody sent their own control out and made the wind to detect this, and then the place.
Right.
And people are worried that you may see more
So why is
attacks on
it?
the algorithms themselves, right? That I change the algorithm and send it over to the network, and then when it executes, it does these wrong things for the actual physics of the system.
I think that the bottom question is not just about security, but it's
Right.
about protocol. The rules, rights, and regulations,
Policies.
right? Policies that you have to exchange this can be audited any time or can be.
You have to monitor those.
You have to monitor. them.
How? How are you monitoring the execution of the control algorithm?
Well, I think it can be related to some of this stuff.
Yes, but as far as I know, it's,
No, there is no
it's
more.
very primitive still.
Yeah, very primitive.
And they all trust each other until you get something like that on the card. Right?
Absolutely. Yeah. So I think in that sense it's very open.
Any other questions? Okay, let's.
Oh,
yes,
there
go
is-
ahead.
So in your letter, one slide, you were talking about how much information should be modeled when you are designing your distributed system, right? And you said there was electrical state, there was a mechanical state, and there was other one. I don't remember. So all of your model were based on those energy state of the system, P and Q, basically, when you showed all those simulations, or you introduced more detailed information when you were modeling.
Detailed information about the conversion and things like that, right?
Yeah, so it was all, essentially was those P and Q that you were, energy consumption by each node that you were modeling in each of your nodes.
So there is a dynamics of, let's say if it's a wind power plant, you can model it as negative load, that's just a disturbance, or you can model it as induction machine, controlled induction machine with power electronics or not, or synchronous machine with some control or not. And then in the model, the dynamics of wind power plant are determined by its own dynamics and also by how much comes in and out in the power plant. So that's the model, right? And we have one student, Nippon Buckley. I think it's been very difficult thesis, but finally we are getting somewhere. That goes to the fundamentals of energy conversion. If I mentioned this ramp rate thing. People say we can schedule knowing that coal power plant can respond, change between two samples only so many megawatts per hour or something. That is a fiction. There is no such ramp rate. It comes from the energy conversion dynamics, from its control and so forth. Like Carl Ostrom and their group, they've been working a lot on controlling combustion engines so that their input-output characteristic looks smooth, right? Looks nice. So you have, depending on load control, you have the ramp rate will change. Nobody actually includes that now in detail. So you do the optimization assuming ramp rate as a constraint, or if you, with these distributed things, you can actually represent as much of detail as you can, but not at a centralized level. So, I mean, it lends itself to different levels of this modeling detail, but I think what's still very hard is, I just gave some examples, but maybe even some emerging behavior where there is such strange interaction between energy conversion and the electrical dynamics and the rest of the system that we don't know, in particular with these small resources, so it's all open. So we just covered some things, and the things that we have covered were existing resources on the islands. That's the closest we come to anything realistic. And we are very happy about this. I just should say that in the book that came out, there is extra. You can go and get all this data about the wind on the islands. You can get the mechanical models, electrical models, the grid wires, and so forth. So I think it's very useful. And we are using it in the course that I'm teaching on smart grids and future energy systems this fall. Yeah, we converted that simple island, which has 3 generators, hydro, diesel, and wind, into sort of 2-bus system, right? Where hydro and wind can be disturbances, diesel can be controlled, or you add hydro, diesel, and carries a long way. You can put a strong connection, just for educational purposes, because we really don't understand these systems behave very differently than the ones that we are used to, the both power systems.
Thanks.
Okay.
Any questions?
Thank you very much.
There will be a informal roundtable here in this room, 4 to 5, or related to this. Professor Ilic, welcome. Let's thank the speaker again.